In this lecture, we will be solving initial value problems using Laplace transform. And the problems that you will see in this topic are very similar or even the same to problems in uh, chapter 3. But instead of using the methods from chapter 3, here we use Laplace transform. Let me recall important properties of the Laplace transform that we will need to use. First is the linearity of the Laplace transform. What it means is if we have Laplace transform of the sum of two functions, we know that the function should be in the independent variable x. But here, let me just drop the x, so it's easier for us to write down. Laplace transform of the sum is the sum of two Laplace transform. And similarly, if we have a difference, and it's a difference. And I mentioned in the previous lecture, here we only have two functions, but it works if we have three functions or four, etc. Another thing is that if we have Laplace transform of a constant k times f, then we can pull the constant k out and we have Laplace transform of f, but keeping in mind that k is a constant. We also have the relation between Laplace transform of derivative and Laplace transform of function. So, for example, Laplace transform of the first derivative is s times Laplace transform of f minus f0. And we also need Laplace transform of the second derivative is s squared times Laplace transform of f minus s times f0 minus f prime 0. Now for the second formula, you should pay attention to these two factors. We have s times f0, and here we don't have any s, and it's derivative. So let's look at some example how we can use Laplace transform to solve initial value problems. The first example, solve the initial value problem. When we use Laplace transform, we always have initial value problems. We have ODE together with initial conditions at 0. Y double prime minus y prime minus 6y equals 0. Y0 equal to 1. Y prime 0 equals to -1. Of course, we saw such a familiar problem back in chapter 3. I think at the very beginning of chapter 3, and we use a different method. For now, we will use Laplace transform to solve this. Let's see our ODE as usual, homogeneous equation, and we have initial condition. Now to use Laplace transform, the first thing we do is we take Laplace transform of both sides of the ODE. the ODE. So what it means is we have Laplace transform of the left hand side equals to Laplace transform of the right hand side. And by using the linearity of the Laplace transform, we can break it into Laplace transform of second derivative minus Laplace transform of first derivative, and then minus 6 Laplace transform of y. Now the right hand side, Laplace transform of 0, we get 0. Now using the formula for Laplace transform of the second derivative and the first derivative over here, the laws are given in terms of f, but here instead of f we have y, but we have the same formula. So for second derivative, we will need s squared times Laplace transform of the function minus s times f0 minus f prime 0. So let's rewrite here. We know that Laplace transform of second derivative is s squared Laplace transform of the function minus s times now y0 minus y prime 0. But well, from the initial condition, we know what y0 is. So we have s times what here? y0 is 1 minus the derivative of y0, which is negative 1. So we have minus 1 here. Let's simplify this. We have s squared Laplace transform of y minus s plus 1. That's the first thing. And then we have Laplace transform of the derivative, also written as s times Laplace transform of y minus y0. Then we plug the values of y0 in. We have s times Laplace transform of y minus 1. y0 is 1. So we have written Laplace transform of the second derivative in terms of Laplace transform of y, Laplace transform of first derivative in terms of Laplace transform of y. Now we will plug into the equation above here, equation star, after we have taken Laplace transform. So we plug into equation star. So we get the, whenever we have the second derivative, Laplace transform of second derivative, here we replace by the entire expression there. And for Laplace transform of the first derivative, we replace by that. And we do the algebra. We need to be careful with the algebra here. So second Laplace transform of second derivative, we have s squared Laplace transform of y minus s plus 1, and then minus Laplace transform of the first derivative, which is s L of y minus 1, and at the end we have minus 6 Laplace transform of y. On the right hand side we have 0. Now we will distribute, and you see that at the beginning in the differential equation we have second derivative and first derivative, but for Laplace transform we only have, after using the formula above, we only have Laplace transform of y, Laplace transform of y, and Laplace transform of y only. That is important. So we distribute in, we have s squared Laplace transform of y minus s plus 1 and minus s Laplace transform of y plus 1 minus 6 Laplace transform of y equal to 0. Now the next step is to solve for Laplace transform of y. Let's look at all the terms with Laplace transform of y. We have this term with Laplace transform of y, this term, and that. We will leave these terms on the left hand side, and at the same time factor the Laplace transform of y out. Everything else we move to the right hand side. So for all these blue terms, after we factor the Laplace transform of y out, we have s squared and minus s minus 6, and everything else we should move to the right hand side. The minus s here, when we move to the right hand side, we have plus s, and then 1 plus 1 is plus 2, but then to the other side we have minus 2. Now for this problem, the algebra is not too bad, but for other problems the algebra may be a little more difficult, and you need to be careful, do the algebra correctly. Now we're going to solve for Laplace transform of y. Then we get s minus 2 divided by s squared minus s minus 6. Okay, after solving for Laplace transform of y, we need to know what y is, right? So what is y? That is the final answer. That's the ultimate goal we're looking for. But this is just the content of the previous topic. Laplace transform of y is the fraction like this. So y is nothing but the inverse Laplace transform of the fraction. And we know how to determine the inverse Laplace transform using partial fractions. So let me do that here. Find partial fractions. We first need to factor the denominator. And as before, if we cannot factor, we have to complete the square. And for this problem, we can factor as s minus 3 times s plus 2. And so we have a over s minus 3 plus b over s plus 2. Clear the denominator. Clear denominators. And solve for a and b. This is very similar. I think it's actually the same problem that I did in the previous lecture. So I'm gonna just write out the answer for you. It turns out that A is, let me look for it. A is 1/5 and B is 4/5. You may pause the video and try to do yourself. So we have the fractions s minus 2 over s squared minus s minus 6 is A, which is 1/5 over s minus 3 plus b 4/5 over s plus 2. So taking the inverse Laplace transform, we have our solution here. Remember that y is the inverse Laplace transform of the fraction here. So then we will have inverse Laplace transform of the right hand side, which gives us 1/5 inverse Laplace transform of 1 over s minus 3 plus 4/5 inverse Laplace transform of 1 over s plus 2. And now we only need to use the table of Laplace transform to figure out what the answer is. Inverse Laplace transform of 1 over s minus alpha is e to the alpha x, so e to the 3x. And then we have 4/5 inverse Laplace transform of this is e to the negative 2x. And this is our solution to the initial value problem. So Laplace transform gives us a different method to solve initial value problem, and it's very different from the method that we learned in chapter 3. We don't need to solve for C1, C2 or anything. Right? The initial conditions are used directly from the formula for Laplace transform right here. So initial conditions are used right here. And that is the only place where we use initial conditions. Where we need to do partial fractions to solve for the inverse Laplace transform. Now let's look at another example. Example 2. Solve the initial value problem. Y double prime minus 4y prime plus 3y equal to 2e to the 3x. What initial condition? Y0 equal to 2, y prime 0 equal to 1. And this time we have a non-homogeneous equation because the right hand side is not 0. But the method will be the same. We're going to take Laplace transform of the ODE. Both sides of the ODE. I want to emphasize that. Both sides. Then on the left side, with using linearity, we can break it, the Laplace transform into several pieces. And let me just write that quickly. So we have Laplace transform of the second derivative minus 4, Laplace transform of the first derivative, then plus 3, Laplace transform of y. On the right hand side, we have Laplace transform of 2e to 3x. We can pull out the 2, we have Laplace transform of e to 3x. Now, we use the formulas. Use Laplace transform of second derivative is s squared Laplace transform of y minus s y0 minus y prime is 0. As I mentioned earlier, you need to be careful about where the derivative goes. The derivative goes in the second, in the last piece here. And we have s squared Laplace transform of y minus s times y0, then minus y prime is 0. Y0, look above 2, and y prime of 0 is 1. We have 2 here, and then 1 there. Meaning that we have minus 2s minus 1. And then Laplace transform of the first derivative is s times Laplace transform of y minus y0. So we have s times Laplace transform of y minus 2. Also, on the right hand side, we have 2 Laplace transform of e to 3x. We know what it is. It's 2 Laplace transform of e to 3x. We have 2 times 1 over s minus 3, or the same as 2 over s minus 3. Now we plug everything into the equation star that I didn't label yet, but this is the equation star here. So we have Laplace transform of second derivative replaced by s squared Laplace transform of y minus 2s minus 1 and minus 4 times Laplace transform of the first derivative, which is s times Laplace transform of y minus 2, and lastly plus 3 Laplace transform of y. On the right hand side we have 2 s minus 3. No, sorry, 2 divided by s minus 3. Distributing, and be careful with the algebra. We have s squared Laplace transform of y minus 2s minus 1 minus 4s Laplace transform of y plus 8 plus 3 Laplace transform of y. On the right hand side we still have 2 over s minus 3. As before, we keep all the terms involving Laplace transform on the left side. And factor out the Laplace transform. So Laplace transform of y times, we have s squared minus 4s plus 3. And everything else we should put on the right hand side. The right hand side we have 2 over s minus 3 already. And the minus 2s here becomes plus 2s. And then minus 1 plus 8 is plus 7. But when we move to the other side, it's become minus 7. Now, we need to use common denominator to simplify this. Let me rewrite Laplace transform of y times s squared minus 4s plus 3 equal to 2 over s minus 3. Now we can think of 2s minus 7 as one term divided by 1. So we multiply both numerator and denominator by s minus 3 to have the common denominator of s minus 3. And we add them up. S minus 3. 2 plus 2s minus 7 times s minus 3. Now over here, you don't need to distribute the numerator and simplify it. Just leave it like this. It turns out easier later on. So don't distribute the numerator. Now we solve for Laplace transform of y. And we have the numerator 2 times 2s minus 7 times s minus 3. And we divide here, we get s squared minus 4s 3 times s minus 3. So before, we need to use partial fractions to determine the inverse Laplace transform, which will give us y. But before doing that, we have to factor the denominator. Don't need to do anything with the numerator for now. Factor the denominator, we have s minus 3 and then s minus 1, that's the quadratic one. And then we also have s minus 3 at the beginning already. And we need to combine the two factors of s minus 3 to get s minus 1 s minus 3 squared. Okay. Now, let's do partial fractions. So let me just do right here as well to save me some writing. The partial fraction will have the form a over s minus 1 plus, for s minus 3 squared, we need to have b over s minus 3 squared plus c over s minus 3. When we have power 2 here, we need to begin with power 2 and then we go all the way to power 1 here. That's actually power 1. Clear denominators. By multiplying everything by the common denominator, and we have on the left side the numerator above, which is 2 plus 2s minus 7 s minus 3 equal to a times s minus 3 square plus b times s minus 1 plus c times s minus 1 s minus 3. You need to do, if needed, you should do the algebra carefully. Look. Now to solve for a, b, and c, we use special values of s. For example, set s equal to 3. We plug 3 in. Now here you see the benefit of leaving the product here. When you put s equal to 3, this product becomes 0. So the left hand side is 2. Then a times 0 square, which is 0, plus b times 2, and plus c times 0. So easily we get that b is 1. Another special value is s equal to 1. This will kill off b and c. When s equal to 1, we plug in here. It's best to do step by step. You just plug in s equal to 1, rewrite 2 plus 2 times 1 is 2 minus 7, 1 minus 3 equal to a. S is 1, so we have minus 2 square, and everything else 0. B times 0, C times 0. From here, calculate this. 2 is in negative 5 times negative 2, 10 equal to 4a. So a equal to 3. Now we don't have any more special values of s. So we can plug in, say, s equal to 0 and solve for c. Another way you could do is to look at the coefficients of the highest order of. So the highest power of s here would be s squared. And pretending we don't need to distribute a FOIL, but if we pretend to FOIL, then we will have s minus 3 times s minus 3. So the s squared will come from here, as squared. Over here, with FOIL, we would have c times s squared. So on the right hand side, we have as squared plus cs squared. On the left side, if we FOIL, we have 2s squared. So then from there, we can solve for c. But either way, we can use special values of s or combine with looking into the coefficients to solve for c. So over here, I'll try set s equal to 0 and solve. It turns out c is -1. Or use the coefficients of s squared. So as I mentioned, coefficient of s squared on the left side, we have 2s squared. On the right side, I mentioned earlier, we have as squared plus cs squared. B doesn't contribute to s squared. A squared plus c s squared. So canceling s squared, we have 2 equal to a plus c, but we know that a is 3 from above, so we can solve c to be -1, the same as before. So that's your choice. You can use either method, but sometimes combining the two methods would give us a faster way. But anyway, so we have found the partial fractions that Laplace transform of y, which is the fraction. Let me not rewrite the fraction. Instead, write in the partial fraction. We have a over s minus 1, and we know that a is 3, b is 1, and c is -1. Rewrite that. 3 over s plus 1, s minus 1, b is 1, so 1 over s minus 3 square, and c is -1 over s minus 3. So taking inverse Laplace transform, we have y equals to 3 times inverse Laplace transform of 1 over s minus 1 plus, inverse Laplace transform 1 over s minus 3 squared, then minus inverse Laplace transform 1 over s minus 3. Now looking at the table of Laplace transform, we get 3e to the x. Inverse Laplace transform of 1 over s minus alpha squared involve x times e to the alpha x, e to 3x. And lastly, we have minus e to 3x. And this is the solution to the given initial value problem. Now, let's look at another example that involves trigonometric functions. So far, we haven't seen that yet. Solve the problems by double prime plus 9y equals to 9, y0 equals to 3, y prime 0 equal to -1. So as before, we need to take Laplace transform of the ODE. And use the formulas for the Laplace transform. Let me write one line here for you to see. Laplace transform of second derivative plus 9 Laplace transform of y equals Laplace transform of 9. And using the formula, now Laplace transform of 9 is a constant. If you look at the first formula, one of the first formulas, you will have Laplace transform of k is k over s, so we have actually 9 over s. And then we use Laplace transform of second derivative together with initial condition above. You may pause the video and count yourself, but let me just this is what we get to say sometimes. And we have s squared Laplace transform of y minus 3s plus 1 plus 9 Laplace transform of y equal to 9 over s. Then we keep all the terms involving Laplace transform on one side and factor the Laplace transform out. So Laplace transform of y times s squared plus 9, and everything else we move to the right hand side. We get plus 3s here and minus 1. Using common denominator, we have 9 over s plus 3s minus 1 times s. So add them up. We have 9 plus 3s minus 1 times s. Now this time the numerator is quite simple. So if you want, you can distribute it. But it's not necessary to do so. Now we solve for Laplace transform of y. We have 9 plus 3s minus 1 times s divided by s squared plus 9 times s. And we need to use partial fractions for this. Now we have two types. The factor of s is a simple factor. And we also have s squared plus 9, which is a quadratic factor, which we cannot factor more, right? So for quadratic factor, we need to complete the square, but this is simple, just s squared plus 9. So it's already kind of like a square plus another square, so we don't need to complete anything. We complete the square when we have s squared plus a constant times s and plus something else. Then we need to complete the square. Now the easiest term is s, just a over s. But for s squared plus 9, it's a quadratic term. We call it the irreducible quadratic. We cannot factor irreducible quadratic. Then we should have b times s plus c. Maybe I should recall. So for we have something like for s minus alpha square plus beta square, we should use b times s minus alpha plus c divided by that quadratic s minus alpha squared plus beta squared. It's not in this example, but maybe in other examples or other problem we need this. Now we clear the denominators. We get that 9 plus 3s minus 1 times s equal to a times s squared plus 9 plus b, let me just write on second line, plus b times s plus c times s. So multiply both sides by the common denominator here, s squared plus 9 times s, and cancel things. We will have this. Now we could say set s equal to 0, special value. We would have 9 equal to a times 9, and everything else is 0, because we have b times 0 plus c, but then 0 here as well. Cancel out. From here we have a equal to 1 easily. Now we don't have any other special values, so we could set s say equal to 1, and then say -1, etc. to find b, c. But as we saw earlier, we may use coefficients. Of say s squared to make the calculation easier. If we use the coefficient of s squared, then we need to distribute. And as I said earlier, we just pretending we're distributing. Then what's s squared? How many s squared do we have on the left side? We have 3s squared. 3s squared. And on the right side, to do carefully, distribute, we have as squared. And then right here, bs squared. And that's all, right? The s times c is not s squared. So we have a s squared plus b s squared. We know that a is 1. Cancel the s squared we have. A plus b equals 3, but a is 1. So b is 2. Because we know how much is 1. Now for c, we could look at the coefficient of s on both sides, but we need to be extremely careful. This is a simpler example, but for more complicated example, we need to distribute carefully because usually the s term involve many other terms. The highest power of s squared only involves a few terms. But in any case, over here we can also go back and to set s equal to 1 and then find c. Either way. And you should try yourself. But it turns out I have done that. And c turns out to be -1. So Using partial fractions, we have written the Laplace transform y as a over s, but a above is 1 over s plus b, which is 2 times s, and c is negative 1 over s squared plus 9. 9, I should write 3 squared. And I split this fraction into two pieces. 2 times s over s squared plus 3 squared. And then minus 1 over 1 s squared plus 3 squared. Now using inverse Laplace transform, we will get the inverse Laplace transform of 1 over s is nothing but 1. And then we have 2 times the inverse Laplace transform of the fraction here. If you look back as the formula of the table of Laplace transform, we have s divided by s squared plus beta squared is going to be cosine of whatever beta is 3x. The last one is a little tricky. For the Laplace transform of this, we have sine. But remember that Laplace transform of sine has a beta in the numerator. In this case, beta is 3. But in the numerator, we have only 1. So we need to divide it. It's 1/3. Sine of 3x. And this is the answer to the given initial value problem. Now in the next video, I will provide another example with trigonometric functions in which we need to complete the square. And this is the end of the lecture here today.